Welcome everyone back to episode 2 of dependently typed data structures in Idris. So last time we looked at our tree, our binary tree, and we looked at creating a verified functor interface as well as creating this insert, which also gives a path for x and t. Today we will also be looking at insert once again, but this time we'll be looking at a data structure, well, not a data structure. We'll be trying to show that given an ordered tree, what we spit back out is also an ordered tree. Additionally, we'll be replacing this path data structure with a new data type. We're going to call it insert. And it's going to show some stronger things than path does, which we'll need actually to show that our tree is ordered. So without further ado, I'm just going to start. So I think the first thing we should probably do is what is an ordered tree? So an ordered tree is a data structure which is indexed by a relation which takes two A's and returns a type. It takes in a tree of A and produces a type. Now, what are the cases for ordered tree? Cases for ordered tree should correspond to the cases for tree itself. So in the case of ordered leaf, an ordered tree which is empty, which is just a leaf, it's always ordered. So we're going to say an empty tree is always ordered. In the case of a branch, actually, yes. So in the case of the branch, we're going to need, ordered. So a branch is ordered if its left-hand side is ordered, its right-hand side is ordered, then we know that, well, actually we need to show that x is greater than everything on the left-hand side. So we'll do that real quick with a new data structure I'll call LTE, which takes in our rel, which takes in our x, and also takes in our tree. And in fact, this we're going to flip rel. So it's if rel is taken to be less than or equal, then flip rel will be greater than or equal. So this says that x is less than or equal, is greater than or equal to everything on the left-hand side and less than or equal to everything on the right-hand side, which should, yeah, that should make sense. That basically is enough to show that it's ordered. And so let's see. Now that we have this LTE, now that we've come up with this LTE type, we need to actually give it a data structure. So we're going to give it exactly that. Again, with our relation, the thing we're trying to show follows that relation, and our tree that we're trying to show. So in the case, again, this is going to be very similar. So less than or equal to leaf, well, that's going to be LTE of rel of x of leaf. So it's always true for leaves. And then for branches, again, what do we need to show? We need to show LTE rel xl, right? R well, actually, we need to show, yes. Okay, so X is LT holds for the left-hand side, LT holds for the right-hand side, and rel holds for X and Y. Then that gives us an LTE of rel X branch Y R. And I think also we're going to need to have this here. I'm not sure, maybe we might be able to get rid of this. All right, so that type checks. And one more thing we need is going to be to replace this path with a new data structure called insert, which basically describes what this insertion does, sort of replicated in the data structure. So real quick, it's also going to be, it's going to take in our rel, we're taking the tree before we insert X. Well, actually, it's not going to take in our rel. It's going to take in the item we're going to insert, the tree before insertion, the tree, and the tree after insertion. So insert leaf, and there might be a better way of expressing this, doing this, but this seems to be the best way. So in the leaf case, if we insert X into leaf, we get a branch of leaf X leaf like we had before. And then if there's two other cases, the case where we insert into the left-hand side of the branch. So if we insert to the left-hand side of the branch and we get L prime, then we should get an insert of X branch L prime Y R. And similarly for the right-hand side. Oh, what's wrong with this? Oh. So I need our branch LYR. There you go. Similarly for the right-hand side, we should get, and this needs to be R prime. We should get that inserting to the right-hand side results in a tree where the right-hand side is replaced with the result of the insertion in the right-hand side. Okay. Now that we've got that, we need to do our insertion function. So one thing I'm going to import is control.order. And so actually, yeah, so now we've gotten rid of this path, and from insert you can show path. If you really want to, you can, maybe as an exercise, go back and make the path data structure from insert. There should be a function from insert x t to t prime to path x t prime. So here I'm just gonna get rid of, so the thing I imported, which was control.order, it contains a interface called strongly connects a rel, takes in a type, a binary relation, and it has one function called order. And order takes in x and a y, which are a's, and it either spits out either rel of yx or rel of xy. So we're going to be using that. So let's add that here instead of our ord instance. And this is going to be the same. So let's x, we're going to have our tree. And actually, real quick, I'm going to have a valid tree instance, which just wraps. Actually, I'm going to put the tree here. or just wraps a tree and shows that it's ordered. It's just a little wrapper. And right. So this valid tree is eventually going to have other things like, like balance, whatever you want to think of that you want to show about a tree. But first, we're just going to have ordered for now. So we have our tree here. We also need our valid tree instance, so valid tree a tree rel, and then we produce a new tree. In that tree, we also need to produce a valid tree instance of what now? Let's see. Valid tree of A, and then tree prime and rel. And we need to produce also, for the purpose of producing valid tree, we need to produce an insert of X tree prime. So let's look at this. So insert X tree valid, so insert impl. Let's case split on tree. Oh, what did I get wrong here? Oh, I forgot an arrow. Case split on tree, and let's look at the leaf case first, because that should be easy. Okay, so in the leaf case, what do we have here? Insert impl 2. So we need a tree. We know that in this case, this tree is going to be branch, leaf, x leaf, like we had the same trees before, so nothing changes there. And what do we have here for insert impl 2? We need a valid tree of a branch, leaf, x leaf. So how to make a valid tree? We need to use make valid tree. Actually, I'm going to extract this out. I'm going to look at that in a second. But first, I think we should immediately be able to make an insert, because insert leaf has this structure. So we should just be able to use insert leaf, no problem. Okay, so that type checks, so that's all good. So we need an ordered tree of rel, branch, leaf, x leaf. So how do we make an ordered tree? We make an ordered tree of branch using ordered branch, which means we need to show ordered tree the left-hand side and ordered tree the right-hand side. Now, since the left-hand side and the right-hand side are leaves, we can just use the ordered leaf constructor for those two sides. Similarly, for LTE, we can just use LTE leaf. So it should be pretty straightforward to make this now. We should be able to do ordered branch, ordered leaf, ordered leaf, LTE leaf, LTE leaf, and yeah, that's it. So now on to the recursive case. It's going to be the more challenging bit. That's going to require actual use of our insert. So let's case split here, case split here, and let me rename these real quick. Ordered L, ordered R, what do I want to call this? What did I call this? L, LT, Y, and then Y, LT, R. So yes, there we go, that's fine. So here we got to decide how we're going to insert X into this branch. And again, in order to do that, we're going to have to use our order function. Oops, I hate it when VS Code does that. No, I want the word of, not ordered leaf. Okay, so there's two cases here. The case where X is less than or equal to Y. Insert impl 1. And the opposite case where X is less than or equal to, Y is less than or equal to X. So let's look at the left case first. So is it, oh, and I want to get rid of this so it doesn't complain. Right. So we need to create our branch. So in order to do that, we're going to have to recurse. And I'm just going to destruct the, what else is here? This is going to be ordered, it's going to be ordered L prime, and insert L prime, make order L, right? And then, okay, so we need to, our branch L prime Y of R, and then our dependent pair, or our pair, which is make valid tree of ordered prime. Actually, I'm going to put that in a new thing again. That was a harder case. And then this should just be insert left, right? Since we inserted to the left, this should be pretty straightforward. We have our insert into XL prime. What was it called again? It's not going to like that. And I need in here. Come on. Oh, what's going on here? Couldn't parse declaration. Did I? Oh, what? Oh. Let's try that again. No, still more? What is it saying? Couldn't parse declaration. Now, what did I do? Did I miss a parenthesis somewhere? Oh, that's what I missed. So, insert left of, where's our insert? It's called insert L prime. There it is. And there we go. So, now we need to show our ordered instance. So ordered branch, and what is ordered branch? It has the ordered left-hand side. So in order to show our ordered left-hand side, we have it here actually. So that's good. That should be pretty straightforward. The right-hand side stays the same. This I'm going to get back to. I'm just going to call it P for now. And then Y is less than or equal to R, which we got from our assumption. So how do we show P? What is P even? P is Y is less than everything in L, or greater than everything in L prime. So how do we show that? Well, we should be able to show that, well, given that sort of Y is greater than everything in the tree, I'm just going to use this abuse notation. And we know, what else do we know? We know that X is less than or equal to Y, so we know that Y is also greater than or equal to x, then if we insert x into t and call that t prime, then we should be able to show that y is greater than or equal to everything in t prime. So let's do that. I'm going to call this insert lemma. It's going to take in our relation. It's also going to take in our, so it's going to take in rel yx, and then it's going to lte rel yt, insert x at t to result t prime, and then we're going to, there we go. So this is exactly what we have up here, just codified as a type. And let's try and improve it. And then this is going to be insert lemma. Oh, what's this about? Oh, impl. So let's k-split on insert. Okay. And let's see, in this case, come on, tell me, Idris, do your thinking. All right, so we need lte rel y branch leaf x leaf. So that should be pretty simple to prove, considering we have rel yx already. So it should be a matter of just using lte branch. lte leaf, and then lte, and then lte leaf. And we actually don't need this. It's trivial. So I'm just going to rename these. I'm going to k-split here. Just thinking. And let's see, what do we have here? So lte rel y branch l prime yr. So how do we show that? So we should be able to do, right, so we need to do lte branch again. We're going to go back to that for the left-hand side. And then p should be given as from our assumption, and r is given from our assumption. So this, what is L prime, lt rel y L prime. So how do we do that? Luckily, we have a function just to do that. It's called insert lemma. And we can give it L. We can give it, or we give it lte. Then we give it L. Then we give it IL. That's it. And then similarly, we do the same here. I'm going to just copy this. Should be pretty straightforward. It's a straight mirror of the left-hand side. So R, IR. And there we go. We've shown, oh, right, I need to k-split on this. Come on, please. Oh. There we go. Forgot to write that out. Okay. So we've shown exactly the above, that sort of inserting something does not change. Well, if you insert something given that y is greater than the entirety of the tree, then if you insert something that is less than y into a tree, you get a new tree, then y should be greater than the new tree, greater than or equal to the new tree. Again, this is piece of notation. Please don't yell at me. So we can use that in P here. So this is x is less than or equal to y prime. Should be insert lemma. And to be clear here, rel is flip rel. But I'm gonna leave that out because I think Idris can figure it out. X is less than or equal to y. In this case, right? That's what we want to show. So it'd be flip rel of xy. That's what this means. And then we have lt rel yt. This is t is going to be L. So that's L LTY from here. And then our insert L prime. There we go. And the right-hand side of this proof should be very similar. So let's do that real quick. Just replacing everything with R. Oh. Basically, that's mostly it. Into R, ordered R. This could be y less than or equal to r prime. This is going to be y less than or equal to x. This is going to be y less than or equal to r. This is going to be insert r prime. This order is going to take ordered r prime. Oh, actually, it's going to take ordered L, but not prime. Ordered r prime. X is less than or equal to y, and y is less than or equal to r prime. This is going to be insert right instead of insert left. And this is going to be ly r prime. And that's, oh, let's see, what's wrong with this? Oh, this should be L less than y. Is it happy now? Let's see. It is happy. So we've shown that given a valid tree and we insert something into the tree, so long as it has a strongly connects instance, it should keep it a valid tree. So that's basically it. Hope you guys sort of got some insight from this. I think the biggest thing was this insert lemma. Yeah, I mean, it's quite a lot we've shown today. I mean, I think next time I'm going to be looking at maybe either delete or maybe balancing. I'm not sure yet. Maybe there's other things I could do. But yeah, thank you all for watching. See ya.